Why is it said that when an object reaches the speed of light, time stops flowing? Even if you were on a spaceship that could accelerate indefinitely, you still couldn't surpass the speed of light. What secret lies behind all this? You should know that light speed, as the top speed of known objects, is around 300,000 kilometers per second, meaning it can circle Earth 7 times in a second. Although for humans, the velocity of light is unimaginably swift, in the vast universe it appears like a familiar homecoming. For example, it takes light 8 minutes and 20 seconds to travel from the Sun to Earth, which means that if the Sun suddenly disappeared, we would have to wait 8 minutes and 20 seconds to know about it. To reach Neptune, which is 4.5 billion kilometers away, it takes more than 4 hours. To exit the solar system, which has a radius of 1 light year, it takes as long as a year. Once we leave the solar system and view from the perspective of the Milky Way, we realize that the light from those distant stars takes a long time to reach Earth. It can take hundreds or even thousands of years. This means that when we gaze at the starry sky, what we see are actually images from the past. Even if we could travel at the speed of light, it would take tens of thousands of years to escape the Milky Way, and reaching other galaxies would be even more out of reach. Moreover, according to relativity, any object with mass cannot exceed the speed of light. It can be said that the speed of light is like an invisible cosmic shackle, firmly keeping us bound to Earth. Since this speed is so special, how did scientists discover the secret of the speed of light? Back in 1676, when Danish astronomer Ole Rømer first measured the speed of light, humanity realized that light does not reach any location instantaneously, but has its own fixed speed. This sparked a relentless pursuit to understand the nature of light. However, Newtonian mechanics' absolute space-time view suggested that the speed of light is also defined relative to a reference frame. For example, when you jump up forcefully inside a fast-moving train, even though you perceive yourself as landing back in the exact same spot, to an observer on the platform, you are actually jumping forward at the velocity of the train. Consequently, for those of us on Earth, the speed of light appears to fluctuate at various times and under different conditions of motion. However, in 1887, the Michelson-Morley experiment completely unveiled the mystery of the speed of light. Initially, Morley's intention was simply to prove that there exists a medium in the universe called ether, which allows light to propagate through space. He believed that if a beam of light traveled in the direction of the ether wind, its speed should increase, and conversely, it would decrease if it traveled against it. But the experimental results shocked the physics community at the time, because no matter which direction light travels, its speed is constant. That is to say, light coming from the front of the Earth and light chasing from the back of the Earth both travel at approximately 300,000 kilometers per second. Even though the Earth moves around the Sun at a speed of 30 kilometers per second, it does not affect the speed of light at all. To explain this strange phenomenon, physicists in the early 20th century, Lorentz proposed a hypothesis of length contraction. He believed that when an object is in motion, its length in the direction of motion shortens, which precisely offsets the change in the light path caused by the Earth's motion relative to the ether. After mathematically deriving the Lorentz formula, Einstein, based on the Lorentz formula, developed the theory of special relativity. He argued that all physical laws are equivalent in all inertial frames of reference, thereby negating the absolute frame of reference in Newtonian mechanics. In parallel, while solving Maxwell's equations, the principle of the constancy of the speed of light was derived. This means that in any inertial frame, the speed of light in a vacuum remains constant, regardless of the relative motion of the light source and the observer's frame. To explain this, imagine emitting a beam of light on a moving train, for those on the train. He ought to perceive the speed of light as the speed of light diminished by the speed of the train. Conversely, for the individual on the platform, it ought to be the speed of light augmented by the speed of the train. However, that is not the reality. The speed of light they observe is indeed 300,000 kilometers per second. This elucidates why it is impossible to attain the speed of light. Even if you are aboard a perpetually accelerating spacecraft, you are simply pursuing the light in front. Although from Earth the spaceship appears to be approaching the speed of light, for the light itself, you remain stationary, and it continues to move away from you at a constant absolute speed of light. According to relativity, our universe is composed of 3-dimensional space and 1-dimensional time, forming a 4-dimensional spacetime. The speed of an object in 4-dimensional spacetime is equal to the vector sum of its speed in space and time. The faster the object moves, the progression of time will decelerate. If you stay motionless at this moment, time will progress at a regular pace. Regardless of your decision, the overall velocity of time and space remains unchanged, only the allocation varies. This is the peculiar effect of time dilation. The film Interstellar vividly illustrates this phenomenon. Due to the intense distortion of spacetime surrounding a black hole, in Cooper's frame of reference, merely an hour might have elapsed. Nevertheless, individuals on Earth might have already lived through multiple decades. This implies that even if you perceive yourself as entirely stationary, in actuality, each second you experience is indeed advancing at nearly the speed of light within the time dimension. Meanwhile, photons are quite the opposite. They use all their speed in the spatial dimension, traveling through space at a speed of 300,000 kilometers per second. For them, time remains entirely motionless, so you are fated to journey perpetually at the velocity of light through the fabric of space-time, much like a genuine cosmic voyager aboard a spacecraft named Time, hurtling at the speed of light across the universe.
You can neither stop nor turn back until the end of time. And within this seemingly constrained fate, there lies a freedom that belongs to us, the freedom to choose the direction in which we move forward. We can choose to stride boldly through space, allowing us to travel further, or we can choose to prioritize time, slowing our pace and rhythm to cherish every wonderful moment in our lives.